Hey guys, welcome to lecture number 14. So today, although the semester is over, but we'll still continue with the Putnam since the Putnam competition will be on February 21st, so why not? All right, so in this lecture today, we will start something new. We'll talk about differentiability, and you will see more qualitative properties of differentiability. I'm not going to go and talk about how to compute derivatives and stuff like that. All right, so the first thing that I will have in mind is what we call these very famous theorems, such as Fermat. So we'll be talking about how should I phrase this as qualitative properties of derivatives. So the study of qualitative properties of derivatives. All right, and here is a story. What do I mean by that? So what I mean is that we will use a theorem such as Fermat's theorem, and then we go further to Rolle's theorem, and then from Rolle's theorem we'll go to the well-known Lagrange's theorem, which is nothing other than the classical mean value theorem. Well, let me put here MVT, the mean value theorem. And then from here, we go to Cauchy's mean value theorem. And then at some point, we'll put this together into one frame, let's say. Let's put it like this. And then the second part, which will generalize the mean value theorem, will be Taylor's expansion theorem. Okay, let me put it, Taylor expansion theorem. So this is what we're going to discuss today in this lecture. Also in the recitation, we'll solve some problems from the worksheet. Anyway, and then separately, I will do convexity. I don't think I'll have time in this lecture because I don't want to do like a big lecture, like 3 hours. We'll discuss about convexity. So that will be a separate lecture. You'll see why is it important for a function to be convex and what can we study with convex functions. All right, so let's get started. First, I like to start with Fermat's theorem. So theorem, and we'll do, so this is due to Fermat, which basically says, as you know from calculus 1, it says that if I have a local extrema, so let I be an interval. So this is a real interval, and suppose that f, the function f defined on this interval and real value is differentiable on I. Okay, and now here comes the condition which is very, very important. If this, okay, I'm going to write it with red. If this point x naught, let's say, is in the interior of the interval I, interior of I, right? So it's not on the boundary. This is important because without this condition, the theorem will just fail. Is in the interior is a local extremum, local extrema, I think, right? You can say. Okay, if this is a local extrema or local extremum point, right? Then the derivative at that point is 0. Then f prime of x naught is 0. That's what you have to know. But pay attention, this x naught has to be an interior point. Otherwise, the theorem will just fail. It's not true anymore. This is important. Anyway, we'll see an example of this. First, I'd like to do all these theorems to discuss them, and then we'll do some applications. Local extrema, you know what it means. It means that f can be a local maximum point or a local minimum point, right? Which is different than global. Okay. Anyway, I'm not gonna. I'm sure you know this stuff, but this is an important theorem. All right. Now the next one, which is due to Rolle. This is basically a crash course in advanced calc 2. The next theorem, which is due to Rolle, and in fact, you can prove Rolle's theorem using Fermat's theorem, says the following. So let I be, again, an interval, a real interval. And suppose we have these two functions. Suppose that, in fact, I would say the following. Suppose that f is defined on this interval I, real valued function, is a function, right? And I take these 2 points, and let's say a, b are in this interval I with a less than b, right, are 2 points, such that the following conditions are true. Okay, and the first condition is the following. F is differentiable on the open interval AB. The second one is F is continuous on the closed interval AB. And the third condition, which is essential, well, this is a little bit redundant because differentiability implies continuity, but it will imply it only on the open interval. So that's why I could have said f is differentiable on the open interval AB and continuous at the points A and B. But anyway, it doesn't really matter. You can write it like this. And the third condition says that f of A is the same as f of B. This is important. Then the theorem says then there exists, let's say, point C in AB on the open interval AB. Yes, at least, well, AC, okay, let me put it like this. There exists at least a point, let's say C in AB, such that f prime of C is 0. That's the Rolle's theorem, right? Okay. Now there is a generalization of this is the classical mean value theorem. So theorem, this is the mean value theorem, which is well known, mean value theorem of Lagrange, let's say. And basically this says that let f define on this interval I, right? And again, I is a real interval. And let's consider an A, B are 2 points in I with A less than B, such that the following conditions are true. And these two conditions are the following. The first one is that f is differentiable on the open interval AB. And the second one is that f is continuous on the closed interval AB. You see, there is no third condition, as it is in Rolle's theorem, but in this case, the theorem says that then there exists at least a point, so at least a point, let's say C in AB, such that guess what? Let me write this condition in this way: f of B minus f of A will be nothing else over B minus A is f prime of C. So that's the condition. This is important, especially when we'll discuss in integrals. We'll see an integral version of the mean value theorem, which we'll call the first mean value theorem for integrals. But anyway, that will be another lecture next week. Okay, so this is the mean value theorem of Lagrange, and this is important. Maybe I'll show some applications of it. Why not? You'll see why this is important. You can solve equations. You can even, maybe I'll do an example for the sequences, and so on. Okay, and now there is a generalization of this, what we'll call the mean value theorem of Cauchy theorem. This is the mean value theorem of Cauchy, which instead of one function, we have two functions this time. So let A be an interval, a real interval, and let's just say we have these 2 points, A, B, and I, A less than B, right? Such that the following conditions are met. Are true, and these conditions are the following. Well, as you can see, there will be something similar in terms of something similar with the mean value theorem of Lagrange. So, but this time, instead of saying that only one function is differentiable or continuous, we'll say that wait, I forgot to say something here. Sorry about that. Not yet. And consider the functions, the two functions. Let's say f and g defined on I and real values, such that the following conditions are true. And of course, the first one, f and g are differentiable. So these two functions are differentiable on the open interval AB, and f and g are continuous on the closed interval AB. Right, then there exists at least one point C in AB such that. And now the condition, as you will modify a bit. If you look here at f of b minus f of a over b minus a, then instead of b minus a, we will have g of b minus g of a equals f prime of c over g prime of c. So let's write this as f of b minus f of a over g of b minus g of a equals f prime of c over g prime of c. So that's the condition. As you can see, this the Cauchy's theorem clearly generalizes the classical mean value theorem of Lagrange, right? You just take g of x to be the identity, and then you'll recover the mean value theorem of Lagrange. Okay, so these are the theorems. There's one other thing that I would like to say here. Well, first let me point out a remark before I say another theorem, which is of Darbu. I forgot to mention that, but anyway, it wasn't that important. So, but let me point out a remark. One can use Cauchy's mean value theorem. To prove L'Hopital rule. Prove L'Hopital rules, L'Hopital-Bernoulli rules. This is how we can derive the L'Hopital rules. But now, before I go and talk about Taylor's theorem, where you will see that everything will be generalized in some sense. Well, at least it will be, we will call Taylor's theorem, which will be a version of the mean value theorem, but for higher order derivatives. But anyway, before we go there, let me just say as a consequence, we have the following theorem of Darbu. Which basically says the following. So again, let I be an interval. And f defined on I and real value is a differentiable function. Is a differentiable function. Then guess what? Then something amazing happens to the derivative. Then f prime, the derivative, has the intermediate value property, has the IVP. And let me just say here again, intermediate value property, which we talked about last week. This is important. So it's not continuous, but almost there. Well, almost or not. All right, now, I don't know if I want to veer towards some problems, but maybe I should just say a few things about Taylor's theorem. And perhaps after that, we'll do some applications. So now let me talk about Taylor's theorem. Well, this will be Taylor. And well, I'm gonna formulate this a bit in the following way. So again, let I be an interval, and let's just say f is a function, is a, let's say n plus 1 times differentiable function. Ouch. Times differentiable function. All right. Okay. Oh my, all these notifications appear now. This is crazy. All right. So we have this n+1 differentiable, n+1 times differentiable function. And let's just say x naught is in I, right? So we have this point in this interval I. Then we can expand, the function f in Taylor series around the point x naught as the following. So pay attention to this formula. Let me write it in this way. F of x can be written as f of x minus x naught to the power 0 over 0 factorial, right, times f of x naught. So the zeroth derivative of x naught, which is f of x naught, plus x minus x naught to the power 1 over 1 factorial times f prime of x naught. As you can see, I recover the mean value theorem at this point if I take the interval x naught. And as you can see, I don't know which one is bigger than which one. X can be on the left of x naught or can be on the right? So it's just a point. Plus, and I keep going with x minus x naught to the power n over n factorial times the n derivative of x naught. And now, plus, I'll have this remainder here. What was let's say x minus x naught to the power n plus 1 over n plus 1 factorial times f n plus 1 n of c, with c, and I'll say between x naught and x, right? So this is the Taylor expansion theorem, right? So this will be what we'll call, let me just write it in this way. So this guy here, this is what we'll call, let's say, this is Tn of x. So this is what we'll call Taylor's polynomial. And this guy here, we'll call this Lagrange remainder. Oh, this one here. This guy is what we call Lagrange remainder. Lagrange's remainder. Okay. And of course, you can adapt this to, let's say, if you want, for example, if you want to apply this to an interval, let's say AB, right? You can apply it, and you can say that f of B is f of A times B minus A plus B minus A squared over 2 factorial f second prime of A, and so on, right? So you don't have any problems in doing this. Okay. So these are the theorems. Like I said, I'm not going to go into convexity that much. I'm just going to stick to these theorems for the moment, and we will see a bunch of applications. So now let me see some applications. For example, let's see some problems. So problem 1, which is a bit classical, but anyway, says the following: let A1, A2, AN positive numbers such that A1 to the power x plus A2 to the power x plus AN to the power x is greater or equal than n for all n and for all x, right? Show that A1, the product is 1. This is a strong statement. So I just got an email from the Putnam, so student registration is now open. So, oh wow, okay.
Is it going to be official and everything?
They say so. Yeah, it's gonna be official. I will share these emails with you. Anyway, I already registered the team for the Putnam. So it's going to be February 21st.
All right.
It's your last chance. So let's see here. How would you think of this problem? Does the number n say something? For example, if you consider the function. So let f of x be this function, right? So a1 to the power x plus an to the power x. Well, you can define it whatever you want. So let's say for real values, and of course, since it's exponential, it's going to be from 0 to infinity, right? But does this condition here translate somehow? This guy here? What do you think? In terms of, if we want to write it in terms of function f? How we can translate this? F of x greater or equal than what? Than f of 0, right? So we have that f of x is greater or equal than f of 0 for all x, real, and anyway, in the neighborhood of 0 if you want. So 0 is a local minimum. So 0 is a local minimum. So by Fermat's theorem, what does this mean? So by Fermat's theorem, this implies what? This implies that the derivative at that point is 0, right? That's what the Fermat's theorem says. And now let's compute the derivative, but the derivative f prime of x is, well, you can compute the derivative of each one of these. And in fact, let me write it in this way. So this would be the sum of ak to the power x times ln of ak, right? And now this would be, so f prime of 0 is nothing else than just the sum from k equals 1 to n of ln of ak, which will transform into a product. So this will be ln of the product of ak. And that's pretty much it. So the conclusion follows. So the product must be 1. You see how strong Fermat's theorem is, so you can use it. So this is just an example. There are plenty of other examples as well. But anyway, I'm not gonna stick too much on applications of Fermat's theorem. Now I have another problem in mind. And in fact, maybe I will show something similar. So another problem in mind, so this is problem 2, which was a Putnam, what was it? Putnam A1 1958. It was a simple one, but it's a nice problem. And the problem states the following. So I'm just going to write it the way it was given in the context, in the contest. So if these numbers A0, A1, A2, and so on, AN, are real numbers satisfying and they satisfy this weird, well, I won't say weird condition, but A0 over 1 plus A1 over 2 plus AN over N plus 1 equals 0. So if this is 0, so then we would like to show that the equation A0 plus A1x plus, so ANX to the n equals 0 has at least one real root, has at least one real root. All right, look at it. So basically it says that the polynomial has at least one real root if that condition is satisfied. I think I saw this for the first time in some Romanian Olympiad back in the day, but definitely it wasn't in the 50s. So how would you approach this problem? How should we approach it? You see, that condition over there, does it ring a bell in some way? Well, I'll do this problem twice. When we will talk about integrals, you will see that this problem would be much easier that way. But anyway. So the question is, can we relate this condition here to this polynomial here, or maybe to something related to this polynomial? That is the question. You see, you have these fractions there. When do we get a fraction from a polynomial?
Well, are we differentiating it?
Differentiating it, but you see, but differentiate what exactly? This is the tricky part here. Like I said, I'll do it twice, also with the integral, because it's easier to look at the integral here, and you'll see like, okay, I'm integrating this polynomial, and then that's it, I'm done. but that would be the argument of using the mean value theorem for integrals, and I don't want to go there. So let's stick to differentiability. So if I'm integrating this polynomial, maybe I should do something else to another polynomial, which, so what should I do? I should consider what? Let me see. So let us consider, let's just say Q of X to be the sum. So I'm just going to write it like this. Oh, and now I'm going to look for something that will, the derivative will give me exactly my polynomial P of X, which will be what? Which will be x to the k over k, right? So ak. So, oh, sorry, x to the, let me start from 0 then. Here it's 0, because I want to include a0 as well. From 0 to n, and this would be a to the k plus 1 over k plus 1. I think that sounds better, right? Because it, right? Okay, let me write it again. So it looks nicer. So x to the k plus 1 over k plus 1. Okay, clearly this is differentiable. So clearly Q is differentiable. And Q prime of X is what? Can you tell me what is Q prime of X? Is P of X, right? So Q prime of X is P of X. Okay, but let's see. Let's look at our condition. What is Q of 0? Moreover, Q of 0 is what? If we plug in, Q of 0 is 0. And what else do we have here? Q of 1 is what? If we plug it in, Q of 1 is?
0.
0 as well. You see, because of that condition. So I have Q of 0 is 0, Q of 1 is 0. So let me write again. So Q of 0 is the same as Q of 1. And moreover, both of them are equal to 0. And now, since I have a differentiable function, right, on R, so it's a differentiable on 0, 1, and Q of 0 is the same as Q of 1 is and 0, look here. Then what can we do? We can apply, so by Rolle's theorem, it follows that there exists let's say an x naught in 0, 1 such that Q prime of x naught is 0. Or you can say P of x naught is 0, which is exactly what we wanted to prove. Which is exactly what we wanted to prove. Right? That's it. Is it clear? It's clear, yeah. Right? You see, I will do this, I will solve this problem again when I will talk about integrals, because it's easier. This is a little bit unnatural to do it, because you have to come up with this polynomial that whose derivative will give me p of x anyway. But it will be easy for me if we look at the equation, right? If I integrate that from 0 to 1, I'll get exactly the expression, right, which is 0. And therefore, it would be much easier for me to apply the mean value theorem for integrals, and the conclusion will be can be derived directly. But anyway, you can play around both ways. Like I said, I'll solve this problem again so that you will see how we can apply the mean value theorem for integrals. Okay. So this was the problem. It was a long time ago, but still, it's a very nice problem. Now I have another problem in mind, which is of similar flavor, and says the following. So problem 3, and this is a more recent problem. This is a Putnam B1 2015. And the problem says the following. So let f be 3 times differentiable. Differentiable function. And here I would like to say, though, this is defined on R and real valued. Such that f has, and this is an important condition, has at least 5 distinct real zeros. Has at least 5 distinct real zeros. Okay. Prove that this, okay, let me write here, f plus 6f prime, so the first derivative, plus 12f second prime plus 8f third prime, right, 3 times, has at least 2 distinct zeros, has at least 2 distinct zeros. Okay. I want you to look at the problem. Think about it for a so how would you approach this? You see, this problem has, how should I say it? It has a clear standard approach. And this is just a particular case of the standard approach. And let me tell you the philosophy. Once you see the philosophy of this problem, it will be easy. And let's analyze here something. You see, we have a 3 times differentiable function. Okay, that's great, because otherwise we would have problems. But anyway, but a very important condition here, a very important information in this is that it has f has at least 5 distinct real zeros. And I have to show that the third derivative has at least 2 distinct zeros. But this is the important condition. So let's write this. So as a philosophy, so f has 5 distinct zeros. So let's say, so f has 5 distinct zeros. All right, let's put them here. Let's say first 0, let's write it like this. Second 0, third 0, fourth 0, and the fifth one. All right, so this is the first one, the second one, the third one, the fourth one, and the fifth one. So as a philosophy, you see, what does Rolle theorem tells me? That between any 2 zeros, we have what? We have a 0 of what? Of the derivative, right? So here, between these two, we have first 0 of f prime, of the first derivative. And then here, I'll do again. We have a first 0, or let's just say a second 0, sorry, of f prime. And then between the third and the fourth one, again, we have a third 0 of f prime. And now between the fourth and the fifth one, we have another one, the fourth 0 of f prime, of the first derivative. And we keep going like this. Again, we go between these two, we have another 0, the first 0 of the second derivative of f second prime. Again, the second 0 of f second prime. And now between these two, I have a third 0 of f second prime. You see, this, if you look at this, the number of the zeros for the first derivative is 4. For the second derivative, it will be 3. And then for the third derivative, guess what? It will be 2. So this will be the first 0 of f for the third derivative. And then from here, again, we'll get the second 0 of f for the third derivative. You see, we apply Rolle each time. So here, Rolle's theorem. This is what we call Rolle sequence, in fact. But anyway, you obtain, so between any 2 zeros of the function, there is a 0 of the derivative, right? Is it clear what I'm doing?
Yeah.
You see, if you look at this, you have 5 zeros for f. Let me put here f. Oh, sorry, f. Then here, let me put f prime. Oh, f prime. Then here, f second prime. And here, f third prime. The number of zeros for, as we take the derivative, the number of the zeros will decrease. Right? So we just apply Rolle's theorem over and over and over again. And now, once you have this philosophy in mind, right, it's pretty clear what we will, what happens. So basically, you just have to construct a function which will fit perfectly with this guy here. And do you remember what kind of functions did we construct where the derivative and when we take the derivative of that function, we'll just take the constants out, and that was pretty much it. Maybe I don't express myself clearly enough. Clearly and vaguely at the same time, so that I wouldn't give you the... But anyway, was there a function in combination with f that will give you something about the derivative? For example, let me be specific. I don't know how to be vague and not to be confusing. So for example, if we take this function, e to the x times f of x, right? So this is what we call the integrand factor. So we have this integrand factor here, and when we take the derivative, let's say, right, it's going to be something e to the x times f prime plus f of x. You see, you have a combination of this. But now if we take the derivative again of this, the second derivative, right, again, you'll have something, so e to the x f of x second prime, which is e to the x f prime of x plus f of x prime. This would be what? If we take, well, we apply the product rule here. So this would give us f prime. So it's e to the x times f prime of x plus f of x plus e to the x times the derivative of this f second prime of x plus f of x. You see again, plus f prime of x, sorry. You see again, so this would be equal to, if we factor, this is f of x, so this would be f second prime of x plus 2f prime of x plus f of x, you see? So I have a combination with derivatives. So maybe I should do, if you look at this here, it's the same thing. F prime to 6f prime, 12f second prime plus 8f third prime. So maybe we should look for some sort of combination between, maybe we consider a function, and when we compute the third derivative, it will give me those exact coefficients. So what should we do here? You see, we have to consider a function e to the x, but maybe it's not e to the quite x, maybe it's a constant k here. So maybe we should consider something like, so in our case, maybe we should consider something like I don't know, maybe h of x is e to the, let's say, a constant kx times f of x. All right. If we compute the third derivative of this, and you have to put the coefficients in such a way that it will give me exactly. So the question is, the big question is, who is that k over there? Well, you can just compute the derivative. Let's do it. So we have h prime of x is e to the kx f of x prime, and this would be, let's see, this will be k. You see, this is why we consider a to the kx, because I'll have that constant there. So it's k e to the kx f of x plus e to the kx times f prime of x. If we factor e to the kx, this will be f prime of x plus k f of x, right? Now let's take this second derivative. So this would be, again, k e to the kx times f prime of x plus k f of x, right? Plus e to the kx times the derivative of this. So it will be f second prime of x plus k f prime of x. And now if we put everything together, if we factor something here, you see I have a k here, but I don't have it here. This would be e to the kx, let's factor. And this would be, let's be careful here. So it will be k f prime. So f prime will have a k plus 1. So f second prime of x plus k plus 1 f prime of x plus, what else do we have here? So it's plus k squared f of x. Right? Did I do any mistakes in computations? Doesn't seem that way, right? Okay. And now let's look for the third derivative. Oh my. And now h third prime of x would be, again, we apply the product rule. This will be k e to the kx times f second prime of x plus k plus 1 f prime of x plus k squared f of x. And now plus e plus e to the kx f third prime of x plus k plus 1 f second prime of x plus k squared f prime of x. And now if we factor everything here, let's see what this will give us, e to the kx times, and now we should be careful. So it's second prime, we'll have a k plus, so it's, so the third derivative, does it have anything? No. So it's f prime of x, the third derivative of x plus, and now let's see for the second derivative. The second derivative has a k and k plus 1, so it's 2k plus 1 f second prime of x plus, and now let's see the first derivative, so it will be k squared plus k, so it will be, so 2k squared plus k f prime of x. And now let's see the last one, so it will be k cubed f of x plus k cubed f of x.
In your second derivative, you have k plus 1. Should it be 2k?
We're here?
Up when you're computing the second derivative?
The second, okay, let's see. The second derivative, where?
The k plus 1 coefficient on the f prime. Should that be 2k?
Correct, it's 2k, shoot. Yeah, it's 2k. See, this is what is 2k f prime of x. And now, so instead of, okay, so and now for the third derivative, so instead of k plus 1 should be 2k, right?
Yeah.
So modify everything here. This is 2k times f prime of x. And also here, 2k. Wait, no, let's keep. Wait, is again 2k here?
Yeah.
Yeah, okay. And now, let's see how, so it's 2k. Yeah, this makes more sense now because, yeah, now it's clearer. And now let's see here. So this would give us, in fact, let's do it again. So this would give us, the third derivative will stay the same. So it's f third prime of x plus. Now let's see for the second derivative. So this is the first derivative here. For the second derivative, we'll have 2k. And wait, do I have 3k? So it's 2k plus k, which is 3k. Yeah, second prime of x, right? Yeah, okay. Yeah. All right. Plus, let's see, for the first derivative, what do we have? So we have 2k squared plus k squared, 3k squared, f prime of x, plus, and now let's see. For f of x, we have k cubed f of x, right? Okay, I think this should be correct. Anyway, so these will have, and now you have to put k so that it will work perfectly. It would fit perfectly into the picture, and maybe k 1/2 will help out. So if you put k equals 1/2, I think everything is perfect here. So you'll have or 1/4. Right? So if you, or 1/8 maybe. Anyway, something like this.
You could do k equals 1/2 and then just factor out a 1/8.
Yeah, exactly, factor 1/8, yeah, anyway. So for 1/2, the conclusion follows. This is how you play with this problem. Is it clear? Jack, is it clear?
Yeah.
So this is the philosophy. So again, and now you're gonna, well, of course you have to do a lot of explaining to this problem, but you see, this is the philosophy here. So you have f, it has 5 zeros, and the derivative will have 4 zeros. The second derivative will have 3 zeros. The third derivative will have 2 zeros. The fourth derivative will have only 1 zero if the function was 4 times differentiable, right? It's clear, right? So this is the philosophy of this problem. Anyway, now let me veer towards something else. So there is another problem that I would like to do. So keep this idea in mind, and now I'm going to do something similar. I would say easier, or maybe. So the problem says the following. So problem, let's say 3, which says the following. See, this was a Putnam B3 in 1994. And it says the following. So it says that find the set. So I'm just going to write it the way it was stated in the contest. So find the set of all real numbers k. Real numbers k. With the following property. And the property is the following. For any positive differentiable function f that satisfies this condition, f prime of x is greater than f of x for all x. I think this should ring a bell. There is some number n let's say n, such that, guess what, f of x will be greater strictly than a to the kx for all x greater than n. Okay. The statement is clear, right? I hope. So how do we approach such a problem? You see, you have this condition here. And f prime, well, you don't have equality, but you have like f prime of x is strictly greater than f of x. So in other words, the problem asks us the following. So let me translate this. Basically, it says that for what k, so the problem asks us what k must f of x exceed e to the kx for sufficiently large k. That's what it asks us to do. So that is a question we should answer in this problem. And if you look at that f prime of x greater than f of x, maybe that should ring a bell. In what sense? You see, in fact, the problem tells you explicitly, because we also have this guy here, right? So maybe we should consider some function which will involve the function f, but also will involve something, an integrand factor, and the most convenient one is the exponential. So let's consider the following function. So consider the function. Always when you have this kind of like inequalities or equalities between the derivatives, and you have this combination between them, you always think of e to the x or e to the negative x or e to the negative some constant times x and so on. So in this case, let's consider this function. Let's consider the function g of x is e to the negative, let's say, x times f of x. Well, what can you tell me about this function? If clearly this function is differentiable, which is differentiable. And if you take the derivative, and the derivative and its derivative is given by so is g prime of x is this would give us what? Will give us, if you take the derivative, so this would be e to the negative x times f of x prime, and this would be e to the negative x times f prime of x minus f of x. Well, what do we know about this? So we know if we look at the condition of the problem that f prime of x is greater, strictly greater than f of x. So this guy is positive, we know that. So this is positive. So what can you say about g? So g is increasing. This is an increasing function. So now if we look at if we, you see, so g of x will be greater than g of the 0. So in other words, for, let's say, k negative, what do we have? We have that, so for any negative k, we have that what? That g of x will be greater than e to the kx, right? For sufficiently large x. Right? So we have this. All right? Then now if, let's say if k is less than 1, so for any k, let's say less than 1, what do we have in this case? Clearly f of x clearly f of x is greater than e to the kx, right? For sufficiently large x. Again, for sufficiently large x. Now the big question is, what happens, so the question is, what happens when k equals 1? That is the big question. So let's think of this. What happens when k equals 1? So when k equals 1, let's look at the function like g of x. What can we say? So so g of x will have so g is increasing, but when k equals 1, if g of x will keep below 1, let's say, right? Right? Say, this is the, we should be careful here. So let's think. So let's see, if g of x is below 1, let's say, right, then clearly f of x is less than e to the x. So for all x. Right, so there's, we don't, and now, so this does not exceed e to the kx, right? So if g of x is below 1. So what can we say? Um, hmm. So what can we say here? So if g of x is below 1, then clearly, okay. And now, so g of x. But now, okay, this is for k equals 1. But for example, if k is greater than 1, does, so let's see, for k greater or equal than 1, does the function f of x exceeds e to the k x? Well, not quite. So for k equals 1, f does not exceed e to the kx. And let's see why. So for example, we can take f of x to be, and this is a pretty classical example for e to the, let's say x e to the negative x, something like this, right? Sorry, minus e to the negative x. And then the derivative of this and its derivative is given by so f prime of x will be, so this would be what would be the derivative of this? So it's e so it's e to the x, oops, what am I doing? Oops, sorry about that. So it's e to the x minus e to the negative x times 1 minus 1 e to the negative x. So this would be f of x times 1 plus e to the negative x, right? So the derivative is this, which is greater than f of x, right? So the derivative is greater than f of x, right? So I came up with a function whose derivative is greater than f of x, but definitely f of x, as you can see, is not, is less than e to the kx for sufficient, for all x. For all x real, and provided that k is greater than 1, right? So for k greater or equal than 1, this doesn't happen. So it will happen only when k is less than 1. Is it clear now?
Yeah.
It's a bit tricky, but anyway, the thing is the same. And all right. Now it's like, oh my God, I'm going a bit over time. Let me do one more problem because I want to show you an application of. So problem 4, an application of Taylor's theorem, and this was it's a deeper problem than it seems at first, and so this was a what was this? So it was a Putnam. What was Putnam B4 in 1958? But I will explain. So the problem says the following. So let C, capital C, be a real number. And let F be a function such that the limit as x approaches infinity of f of x is c, the limit as x approaches infinity of the third derivative of x is 0. And now, so of course it's a three times differentiable function. Prove that the limit as x approaches infinity of f prime of x is 0, and the limit as x approaches infinity of this of f second prime of x is 0, where the superscripts denote the derivatives. Okay. Anyway, this is a just a particular case of a much more general the theorem of Littlewood. Well, I will talk about it, which was published, I think, in 1910 by him. And it's some kind of a converse of so-called Abel's theorem. You see, now you have a relationship between derivatives here. So you go all the way to a third derivative. So how should we approach this? So let's see, because it's a bit tricky. So now, so our intention is to apply Taylor's theorem. So now, so we want to apply Taylor's expansion theorem, and we should be careful here. All right. So now the way we're going to do this, so I'm going to write in the following way. So now, by Taylor's theorem, and we see we can go only all the way up to the third derivative, no more than that. So we should be careful with this, right? As you can see here, we have the third derivative, right? Look at it here. So we cannot go further than this. And we have so let's see here. So by Taylor's theorem, we can say that for any x, right, there exist numbers, let's say, how should I denote it? Denote them, let's say, okay, let me do it a fancy way. C of x and nu of x, right? So in this way, between 0 and 1, right, in the interval 0, 1, such that the following will hold true. And I'm going to write the following Taylor series expansions. So look, the first one will be f of x plus 1. This can be written as f of x. So, right, times f prime of x plus 1/2, so I expand around 0, f second prime of x plus 1 over 3 factorial 1 over 6, right, times f third prime of, and now I'm going to write here in this way, x plus c of x. So I can write it in this way. And the second relation, I can write this as f of x minus 1. So now I'm, you see, it's a, okay, let me write it, then I will explain it. So this is f of x minus, this time, f prime of x plus 1/2 f second prime of x minus, now, you see I'm alternating the 1/6 f second, third prime, sorry, of x minus nu of x. You see, it's the same thing as Taylor expansion theorem, right? The only thing you instead of writing x, f of x, you say x, you write x plus h times x naught, something like this, right? And you get this. So this is a trick on Taylor's theorem. And now, well, what can we do? By adding up these two, so adding up 1 and 2, we get the following. Let's write this, let's say 3, and let's see, what do we get? We should be careful here, so let me see. Okay, so we have that you see, the second, let me write it in this way. So the second derivative, f second prime of x, is f of x plus 1 minus 2f of x plus f of x minus 1, and now minus, let me write this with 1/6 f third prime of x plus c of x, right, plus 1/6 f third prime of x plus nu of x. Okay. And now we subtract 2 and 1. So subtracting. So you always, when you write two Taylor series, you can play around with. You can add them, you can subtract them. So subtracting 2 from 1. And we get, and we rearrange a bit. So this would be what? Let's see, 2 from 1. So 2 from 1. So, okay, you can write the first derivative, 2f prime of x. So if we subtract 2 from 1, is f of x plus 1 minus f of x minus 1 Okay. Minus, and let's be careful here, 1/6 f third prime of x plus c of x minus 1/6. Please correct me if I'm doing wrong computations. F third prime of x plus nu of x. Okay. So let's call this 4. All right, so we have this. So 1, 2, 3, and 4. Let's look at them. So what can we say here? As x approaches infinity, because we're interested in that. So as x approaches infinity, what can we say about, so x plus c of x and x minus nu of x approach infinity, right? That's obvious. All right. So all terms in 3 and 4 have finite limits. So all terms in 3 and 4 have finite limits. Right? And now we can write in the following way. So we can write the second derivative. So we have the following: f second prime of x, and in fact, let's put the limit in front of it. We have that the lim as x approaches infinity of f second prime of x is, and we should be careful now. Let's replace. Let's see, what do we know? Let's look at 3 and 4. So 3 and 4, and we know something about the limits. Let's go back. So what do we know? Look, we know that some of them are 0. So we know that f of x is c, the third derivative is 0. So let's be careful here in 3. So it's c minus 2c plus c minus 1/6 times 0 plus 1/6 times 0, right? So this would be c minus 2c. Let's look again. So c minus 2c plus c minus 1/6 times 0. Right? The third derivative, look there, we have the limit is 0 times 0 plus 1/6 times 0, which will be what? 0. Perfect. And now if we look at 4, the lim as x approaches infinity, the derivative of f prime of x will be what? Well, if we divide by 2, so this would be 1/2 times c minus 1/6 times 0 minus 1/6 times 0. So this would be, if we look, 0. And that's it, we're done. Is it clear? Jack, it's clear, right?
Yeah, that was a fun problem.
Very fun problem. And in fact, the Littlewood's theorem, let me point out a comment, and I'll stop here after this. So remark, the condition on f prime of the third derivative, right? The condition, this limit can be weakened. To f bounded. So it's sufficient for f just to be bounded. And this is a theorem of Littlewood. In fact, it was proven that, well, for Littlewood, it was, he proved it more generally for functions which are k times differentiable. And he proved that the same theorem, right? Imagine this problem for for the n for a function's n times differentiable, and he relaxed that condition for the third derivative, so the limit to be 0, and he replaced it with only f to be bounded. And he published this paper, I think, and the paper is pretty famous. It's called the Converse of Abel's theorem. And he published, I think, in Proceedings of London Mathematical Society, I think in 1910 or 1911. Anyway, this would be, I think you can find it on the internet. All right, I think I'm going to stop here. Thank you.